So our glycogen metabolism learning unit has a fairly short section on mechanism because really we're only talking about two things, and that's the breakage of a glycosidic bond by phosphorylase or the synthesis of a glycosidic bond by synthase. So we're going to look at two mechanisms that sort of relate to that as they relate to phosphorylase and then synthase. So one of the things we're going to do is, because glycogen is kind of a very large molecule compared to what we did with glycolysis, is we're not actually going to show those full structures, but I want you to be able to sort of think about how this works if it was glucose monomers that are cyclized, polymerized into glycogen. Okay, so let's first talk about the chemistry that happens with phosphorylase that's going to be breaking glycosidic bonds in glycogen to liberate glucose 1-phosphate. So here again, we've got in this case, it's going to be an acetal. So let's take a look at this anatomy. So we've got a carbon that's hooked to an OR group, and then in an acetal, it's going to be hooked to another OR group. And this again is going to be an acetal because of this hydrogen that's here. So here's how this maps on. See if you can see those structures from our glycolysis sort of mechanism. When we had, this was an OH group here, when we had a cyclized sugar, and that's the anomeric carbon. Well, when we've hooked this, or we've not just cyclized this, but we've actually connected this to another sugar, this becomes our OR. So this is another sugar that we have here connected to our cyclized sugar. Okay, so this is our glycosidic linkage. We call this our anomeric linkage. This is our glycosidic linkage. So when we are talking about breaking down glycogen, we're talking about breaking those glycosidic linkages. So here's the bond that we want to break. The strategy is the same for what we talked about with ring opening. If you want to break a bond, you have to think about, how can I facilitate that bond breaking? Essentially, one of those atoms is going to be a leaving group, and we can make it be a better leaving group by protonating it, knowing that these electrons are going to go to that oxygen, and if we've protonated it, that just helps to pull those electrons and stabilize those electrons because they're going to be favorable there on that protonated oxygen. Okay, so here's our acetal. Okay, so again, our cyclized sugar, our glycosidic bond that we're breaking, so we're going to protonate this oxygen that is the oxygen of our glycosidic linkage, makes it a good leaving group. So just like we saw when we had sugars that we linearized, we're basically going to be opening or using these electrons within this lone pair of oxygen, and lone pair of electrons on oxygen here, and we're going to be breaking that glycosidic bond. So now we've broken this bond, okay? And so we've generated something that is very electrophilic. This is an intermediate that we're going to have here. This is going to be something that doesn't just kind of stick around here. So we are going to have water come in here, nucleophilically attack. Water's a good nucleophile. Not a great nucleophile, but the fact that we have a very electrophilic intermediate here is going to allow this to come in, nucleophilically attack, whether we protonate or deprotonate, beforehand, or we deprotonate after it's already added. This is how we're going to get back to our hemiacetal form. Okay, so that's the mechanism for how we would cleave a glycosidic bond. So if you want, kind of see how this is our cyclized sugar, look back at the glycolysis mechanism. Let's say, we know that this is G1P that we'd have from the breakdown of glycogen, but go and look at for glycolysis. This is G6P that would be ring opened. We don't do ring opening here in glycogen metabolism, but here is kind of that starting point, a cyclized sugar. So what I'm going to map on here now is how this uncatalyzed mechanism becomes a little bit different when we talk about what happens in the enzyme active site for phosphorylase. Okay, so what is different is what we have as our nucleophile. Okay, what we have as our nucleophile is not water, we actually have phosphate. Let me just go for a quick second here to our structure of the enzyme active site for phosphorylase. So here's glycogen phosphorylase. Okay, so let's see if we can map this on here. So I guess this is the best way to actually take a look at rather than drawing out our structures. So remember, we had, here is essentially our acetal as our glycosidigly linked glucose polymer here. So the first thing that we're going to do is we're going to protonate this oxygen, make it a better leaving group. We're going to have an internal nucleophile, push those electrons out. We're going to, again, break this bond. It's made into a better leaving group by protonation here. Okay, so now we have this very electrophilic intermediate here. Okay, so now in our mechanism that we had, I'm going to show you how this is different. What happens now is we're going to have phosphate as our nucleophile. Nucleophilically attacks, but that's why we don't get free glucose. We get glucose with a phosphate on the 1 position here. So here we have glucose 1-phosphate. Okay, so let's go back to our mechanism here. And so what we have is when we have not water acting as our nucleophile, which would give us free glucose, we've got phosphate acting as our nucleophile. Here's our phosphate, right? So we're going to have one of these oxygens here nucleophilically attack, do the same chemistry here, but now that this is going to be an O-phosphate at that 1 position. So that's how we get glucose 1-phosphate when glycogen is broken down by phosphorylase. Okay, so I think that's all that I wanted to say there for our cleavage of glycosidic bonds by phosphorylase. Let's look for a second for the formation of glycosidic bonds. Okay, so this is essentially doing the reversal of this last step. Remember, we've kind of highlighted this before. When we reverse chemistries, it's not just like we write it in reverse. Anytime there's a protonation, it's going to be a deprotonation. Arrows might move in the opposite direction. Okay, so now we have a sugar here. This is a cyclized sugar, so this is going to be one that we're polymerizing to something that's already growing. So what we're going to do here is we are going to protonate this, okay, because we want this guy to go away, generated a very electrophilic intermediate that now is not going to have water as its nucleophile coming in, because that would just take us back to here. It's going to have our alcohol come in. Now, generically, that alcohol is going to be ROH, as we learned in our mechanism, but what we're going to see is that OH group is going to be the C4OH group of a glucose residue. So we're going to review this here, and then we'll map it onto what we see happening with synthase chemistry. Okay, so we want to essentially swap this guy out for an OR. So to make a leaving group, to make something leave, to make a bond break, we protonate it, make it be a good leaving group. Gets pushed out by an internal nucleophile there. And now we're going to have a very electrophilic intermediate that's now going to have our alcohol come in. Now again, whether you deprotonate your alcohol on the way in or you let it do its chemistry first and then deprotonate it, we generate our acetal here. Again, that is our polymerized sugar, because if this ROH group is the C4 hydroxyl on another glucose residue, that's how synthase is going to use that glucose to synthesize our polymer. So again, it's highlighting that synthase here is going to use this chemistry to generate an alpha-1,4 glycosidic linkage for our linear chains in glucose, but our branching enzyme is actually also going to do this same chemistry, but now it's going to be the C6 hydroxyl group that's going to generate our alpha-1,6 branches. Okay, one other thing to map on to kind of relate to things that we see with synthase chemistry is if we want this guy to be a good leaving group, yeah, you could protonate it and you could have water leave, but what we actually see in synthase chemistry is we don't have just regular old glucose. We've got glucose that has a great leaving group as an NDP sugar, a nucleotide diphosphate sugar. Remember how we actually do our coupling chemistry, and I'll go back to the slides to review this with synthase, is we have a growing glycogen polymer, and then the monomer that we're going to add is not glucose. It's actually glucose, it's UDP glucose. It's glucose with a UDP great leaving group, okay? So now that we sort of see this chemistry, this is sort of the review piece, let's map that on to what we see with synthase chemistry. So let's find our synthase slide here. Here we go. So glycogen synthase. So here's our growing glycogen polymer. Okay, so here's a glucose residue that has a free, this is just an acid or a hemiacetal. It's not formed its glycosidic linkage yet. So it's got an OH group that is free to do it's nucleophilic chemistry. So this is the C4 hydroxyl group. Okay, this is the monomer that we want to add. So the monomer that we want to add doesn't start out as free glucose. We don't have free glucose that had an OH group here that we protonated it and made it into this leaving group. Water's an okay leaving group, but an even better leaving group is a nucleotide diphosphate. So we have this activated monomer. And maybe you remember, let's just go back real quick just to kind of highlight. We take glucose 1-phosphate, that's not even a good leaving group, that phosphate, and what we do is we actually activate it. That's what UDP glucose pyrophosphorylase does. That's our activation step when we're doing our synthesis chemistry. We generate a glucose that's like a super coupling glucose because it's got a great leaving group that we have here. So that's what this guy is. It's a glucose with a great leaving group, so that leaving group leaves, we're left with a very electrophilic intermediate. Nucleophilic attack by the C4 hydroxyl of our growing chain polymer generates our alpha-1,4 glycosidic linkages. Now, just to highlight here, if this were the branching enzyme and it were generating alpha-1,6 glycosidic linkages, this would be the OH group that would be used. Okay? So coming back here, I don't think there was anything else I wanted to say, but just let me go back to this slide and make sure that I take a look here. Here's our mechanism slides. Yeah, so that's why we have to have that activated sugar. It's got a UDP good leaving group. All right, so that's it. We really didn't do a ton for mechanisms for glycogen metabolism. It's basically just breaking our glycosidic linkages with phosphorylase or synthesizing our glycosidic linkages with both synthase and then the branching enzyme, depending on which OH group we're using in our sugars. All right.